Hello. We're going to look at the double slit experiment, and we're going to look at it in terms of the actual waves as they travel from the two slits to what we call a screen. That could be a piece of paper. If it's sound, it could be a wall it's hitting. So we've got our two slits on the left and our piece of paper on the right. Let's look at a point on the screen. Now obviously when there's two waves go through here, two slits, they spread out and they meet at all the points on the screen. But we just want to look at one of them at the moment, which is in the middle. Those two arrows there, which show from the point on the screen back to the slits, they're called the path lengths, and the length that wave has to travel to get to that point. So let's just project these waves along and see what happens when they get to that point. Notice that they're in phase and they continue to be in phase. So when they get to that point on the screen, the two peaks line up and the troughs line up. And so what you get is constructive interference. If it's light, it's a bright spot. Now this makes sense because the distance that they had to travel, those path lengths, are exactly the same distance. The difference in them, the path difference, is 0 because the path lengths are the same. So if you took one of those arrows away from the other, you'd get 0. Now with the waves that have started there, looks like they go peaks then troughs. What if we flip them around the other way? So we flip them like this. Would that make a difference? Well, it turns out it doesn't. They still get there in phase, even though it's a trough that gets there. It's two troughs that line up. It's constructive interference. It's still a bright spot. So what if we look at another point? So I've chosen a point a bit higher on the piece of paper. If I draw my path lengths, you'll notice that the bottom path, the bottom wave has to travel a longer path. And what does that mean, that it has to travel a long path? Well, let's have a look. If you follow the waves, because the bottom one travels a longer path, by the time it gets there, it's out of phase. So its trough lines up with the top one's peak. You get the half a wavelength out of phase, they destructively interfere. So the peak and the trough cancel out. When they cancel out, you get a dark spot. So let's look at these path lengths. If we line them up beside each other, cool animations, we get, line them up right beside, put a wave on there, and you see that the difference in those two arrows is half a wave. And that's why they destructively interfered, because the one on the bottom, the path length on the bottom, that wave had to travel half a wave further. So by the time it got there, it was out of phase. So when the path difference is a whole number of wavelengths, constructive interference occurs. When the path length is, path difference, is a half number of wavelengths, then we get destructive interference because they cancel out, and that's a dark spot. If it was sound, it's a quiet spot.